draws a big well. That works too.
Closer to the dark scale, but
All right, let's take a look at your packets. Any of these that you would like to look over?
So I finally do my homework when I got to it. Nope. 19.
Number 19.
that's why I didn't want this.
Okay, let's take a look at number 19. Okay, we'll just check this. There we go. All right. We've got a table. It's got F and F prime in it, so that would be, we've been doing quite a bit of work with tables here lately, so that's kind of a good thing. What's that? Oh, okay. We got F, F prime. It says the line tangent to the graph of F and parallel to the segment between the endpoints intersects the y-axis at a point. So, to me, when I read that, a lot of words in there, but the ones that stand out to me are tangent line. Write the equation of the tangent line, because then I could see where it intersects the y-axis, which of course is the y-intercept. So if I could write the equation of the tangent line, well, I know to do the equation of the tangent line, I need a slope, I need a point to write the equation of the tangent line. Well, it's parallel to the segment between the endpoints. It means it has the same slope as the slope between those endpoints right there. And it says from -2 to 10. So if I did 26 minus 2, -2 minus 10, do the subtract the y, subtract the x's, I get 24 over -12, which is -2. So the slope between the endpoints is -2. So the graph I'm looking for has to also have a slope of -2, and that would be this one right here, where f prime is -2. So my point is 423. My slope is -2. Go ahead and distribute that through. I get -2x plus 8 plus 23, which is -2x plus 31. That would intersect the y-axis at 0.31. Okay? So, tangent line. See what you started, Daniel? All right. All right. He was at a college class at least. Your only excuse is you went to a slow place for lunch. I mean, that was. All right. What's next? What's next? Another one?
26.
26. Was that one we skipped?
You didn't tell us that you just did.
Oh.
You told us to just do them all, and if we couldn't do them.
Well, that's true. I guess I told a few people individually. Somebody asked me about it, didn't I? Derek did. Okay, I was going to say, so I thought a few people asked me. Anything that talks about volume of a solid, that's a chapter 7 thing. Okay, volume of solids, revolving solids, things like that, that's a chapter 7 thing. There was one other one that we couldn't do. So if I didn't tell you to skip it then, and I'm asking you which ones did you have question on, I'm hoping there's another one that you couldn't do, you should probably be asking about. That would be number 20.
20, I was going to ask you about that one.
Okay?
I was confused.
Now, I actually haven't worked it out. You could probably, now I take it back. To say you can't do it, again, and I think I've mentioned this before, since it's multiple choice and you have those other options in there, there are some things you could do. But this is another Chapter 7 thing. Remember yesterday we did our review of differential equations, and we said there's some you can't solve. Well, that's what you have right here. They tell you the slope of the curve, which would be y prime, is this 4xy. So there's a differential equation. They give you an initial condition. We will learn in Chapter 7 how to solve this one and get one of those answers. But the way it stands right now, you could do the derivative of each of these and see which one fits in. Okay? And you say you got C as the answer? If I try to do the derivative of C, 4 would just sit there, so I'd have 4e to the 2x squared, and then times the derivative of the inside, which would be 4x. So now let's see if that matches up over here. You'd have 4x, and then y would be what? Well, y would be this, right? So that'd be 4e to the 2x squared. And sure enough, those two are the same. So it looks like C is right. So you could have got that just by checking some stuff. But we will learn in Chapter 7 how we could have solved that directly. Okay? So good job if you got that one. Any others? How about the free response? Oops. If there aren't any more in the multiple choice. I was trying to think of one we did in the other class. 28. How was that one? No, 28 wasn't too bad. Oh, how about 25? Yeah, that was the one that somebody asked about in the other section. What about 25? Yeah, did anybody do implicit differentiation on that one? Now, it's good to understand that implicit differentiation might be necessary in some of these problems. This one looks like one where it would be. It turns out it's not. You could take a y out. Actually, you don't even have to take a y. So you can just put those together as 2x squared y equals 6, and then just solve for the y. You get 6 over 2x squared, which is y equals 3x to the negative 2. I mean, it really simplifies down that easily. Most of the time they don't, though, on those. And most of the time you have to do an implicit differentiation. So see, now your y prime is negative 6x to the negative third. Your y double prime is 18x to the negative fourth. You put a 1 in for x, you get 18, and there's your answer. So that was the much quicker way to do it. But it certainly doesn't hurt if you went through the implicit differentiation and found the answer that way. And it involves a product rule and so forth, so on. That's fine. If you did that, that's good practice, because I promise you that is going to show up. All right. How about free response number 2? Now, I don't want to waste everybody's time in looking at some of these if you didn't have any difficulties with them, but oops. Or maybe you didn't even do it. Did everybody get number 2? Okay, all right. Seeing some work. Seeing some why it was going on. So, let me just make a couple comments then about some things on here. S is the rate sand's going in. What I like about this question is this seems to have been showing up a lot on the AP test the last 5 years probably or so. Where you have sand coming in at a certain rate, you have sand going out at a certain rate. Whenever you see rate per hour, hopefully what you understand now, the integral would give us what? Amount of sand, right? The net amount of sand over a certain time period. And the nice thing about these calculator ones is all we have to do is set up the integral, and then we can use our calculator to do it. So in part A, when it says how much sand is put into the bin during the workday, you just write out what? It's that easy. And since S of t has already been defined for you, you don't even have to write that. You just write S of t. So put this on your paper, and then Boom, there's your answer. That's how much sand went in. What if the question would have been, how much sand is in the bin? Of course they wouldn't because it's coming out too, so we have to take that into account. But what is another thing you'd have to consider that net amount business? How much was in the bin at the start, right? Now it says it's initially empty, so how much went in is also how much would be in it. That is assuming that came out. Yes, Zach, question.
When they give you like capital S&T, how do you show antiderivative?
You wouldn't, because number one, I don't think we really need to.
Because don't you have to solve for C to set it equal to 0 when time starts?
Are you talking about for part A?
Yeah.
All you have to do is this right here and type it into your calculator.
Oh yeah, because C is arbitrary, so it will cancel out, right?
That's right, because when you subtract them, the C would cancel out. Absolutely. Now, but that's a good question. What notation would you use for if they give you capital S? My guess is they never would do that. If for some reason you needed an antiderivative, they wouldn't do that to you. And so don't be confused by that just because big S, and it's a rate, and so just do that right there, and that's the net amount of sand that comes in. Now, big S minus big R. What'd you say there? Explain what this means. Well, big S of 6 would be what? Not how much. No, S is a rate. The rate that it's coming in at 6 hours. And R is the rate that it's going out at 6 hours. So what's S minus R? The net rate that it's changing. Now, it could be increasing, right? It depends which one's bigger, right? It depends if it's coming in faster than it's going out, or vice versa. So I would just say changing. So this would be the net rate that the amount of sand is changing. The net rate that the amount of sand is changing. Depends which one's bigger, right? Which, of course, makes sense. If S is bigger, then that will be a positive number. It's increasing. The amount of sand is increasing. If R is a bigger number, that value there in the box will be negative. And so, therefore, the amount of sand will be decreasing. I'm curious what you think on C. Explain why the maximum amount of sand in the bin is when S is equal to R. Somebody want to take a crack at explaining that, Zach?
Because are we assuming that S starts out faster and R progressively gets faster?
That's a great.
That's what I did for my answer.
Go ahead. Go ahead with
Because
that.
if we assume that, then the sand's increasing faster than it's taking out until the point that they become equal, and then the taking out becomes faster. So it's increasing, but slowly decreasing the rate that it's increasing, and then it hits the maximum, and then it starts decreasing the same.
It's hard to clearly explain that, isn't it? And to write it out in words. And you're right. Not only could the maximum be when those are equal, but also the minimum, right? I mean, if it was the other way around, right? If the sand was coming out faster, and then all of a sudden it started coming in faster, the sand would start going back up, and then you'd have a minimum amount of sand, right? But I think it would be good enough in this question to say the maximum amount has to be when those are equal. They're not saying that when those are equal, it's a max. You see the difference in those two? When those are equal, is it a max? Well, no, it could be a min. But what they're saying is, when it's a max, doesn't that have to be true? And that would be true, because when the amount of sand is a max, think about it. If S is bigger than R, that sand is going up, going up, going up. As soon as S and R are equal, it'll level off. And then when S is less than R, it'll go down. So when it's a max, it has to be true that those are equal. So I'm not even sure it's important to say that thing you did at the beginning about assuming S is bigger. I mean, you get what I'm saying? I mean, I think that's the assumption that when it's a max, that's what's going to happen. Okay. Now, here would be a more mathematical way. And if you look in the answer book, that is, what you just said is one of the acceptable answers. I would like to talk here just a minute about a more, well, let's do this since I'm recording this. I would like to talk about a little more calculus way of explaining that as a max and see if this makes sense to you. Go back to question 1. Or A and B, parts A and B. If they want the max amount of sand in the bin, sometimes in these questions they will ask you to write a function for the amount of sand in the bin. So let's pretend they had asked me that. Find a function, we're going to call it big A of t, that represents the amount of sand in the bin at time t. Okay? Now think about what we did in part A. Think about what we said in part B. Somebody want to tell me what I would write here? No. Because S is a rate, and R is a rate, and this is supposed to represent amount of sand. You need an integral from 0 to t, S of something besides t, right? I graded AP test about 3 summers ago, and there was a question like this. And if you had t in here, that would be wrong. You need something else. The question had said, write a function a of t for the amount of sand at time t. So you had to use a t here, which means you have to use a t here. Okay, so far so good. Remember, isn't that what we did in part A? How much sand has come in during those 9 hours? Well, that'd be the 0 to 9. Well, we're saying at any time. Okay, keep going. Oh, just as I said, you had to use something besides t, and then 5 seconds later I wrote t. Thank you. Yes, that had to be an X. Then what? You actually probably could put 0 and get away with it because it didn't really start coming out until 1. So from 0 to 1, how much would have come out? None. However, they give you a function for R, and it probably has values from 0 to 1. So to be honest, in this case, you probably couldn't put 0 and get it right. You probably need to have a 1. Okay? So you need to be prepared to be able to do this, because there are times in problems like this where they ask you for that. This would be a function that at any time t would give you the amount that it is changed by, right? The increased amount. So since the bin started empty, this is going to give us the amount at time, the amount in the bin. What if there had been, what are our units here? Cubic meters. So what if there had been 100 cubic meters in the bin at the beginning? What would we do with this? Plus 100, right? Because that's cubic meters. If there was 100 cubic meters in the bin at the beginning, we would just tack on a plus 100 here. Okay? All right, now, let's go back to question C. Question C says, when is the max, right? Where's there a max for the amount of sand in the bin? Well, if this is our function for the amount in the bin, then where do we look for its max? Where the derivative equals 0, right? Okay, let's do it. What's the derivative of this right here? S of t. Remember those problems? The derivative of this, which means antiderivative, is actually this, but with a t plugged in. Okay, minus, what's the derivative of this? What about that 0 and that 1? Doesn't that matter? The 0 and the 1 is just the plus c, right? When you do the derivative, the plus c would go away, so those don't matter. And we want to know when the derivative equals, oh, when does that happen? When S of t equals R of t, correct? So that would have been another way to show that the max has to occur when S of t equals R of t. Okay, I like your explanation because it really shows that you're getting a sense of what the problem is saying. But I really would want you to see this as well. Okay. Well, anyway, let's go ahead and move on here. You need your calculators out. And we're going to pick this person who has a connection error. David,
What?
don't you have a connect? Are you logged in?
I wasn't on
Okay. Do you have battery?
the phone. It was red.
All right. I suppose those are our people that are gone. Jordan and Alex. Okay. All right. Who's this? Derek. Ah, you've been presented before. Dan. Hasn't he been presenter before too? You really have to do that. Who? Ellis? Tori. All right. Now, first, before we get to Tori the calculator, all right, get your notes out. We're going to pick up where we left off yesterday. Okay. We're going to pick up where we left off yesterday with differential equations. We did a slope field, and we talked about how when we do a slope field, that is an approximation of the answers to a differential equation. And of course, the answers to a differential equation are the original function, the original y values. And so when we plot the solution of differential equation, we're looking for those original y values. Well, if we just go with the flow on our graph, it's very rough. I mean, we're just guessing about where those y values are. What we want to do is we want to be much more specific about that and get a better approximation of those y values. Again, because some differential equations can't be solved. Just like some functions don't have antiderivatives, so we can't do integrals with fundamental theorem. So there is a connection to how we're going to do this. So the way we do it is called Euler's method. Euler, not Euler, Euler's method. Now, Euler's method is just a numerical way, and it's hopefully it's going to make a lot of sense to you. It's pretty easy to follow. We're going to do a problem up here. We're going to do this problem here. Y prime, so one we started with yesterday, I think. Y prime equals 2x. We're going to get an initial condition. Oops, that's not the right one. We do y of 0 equals 1. Now, I think we all know what the solution to that's going to be, right? What's the solution to that differential equation? X squared plus some c, which we'll then put in our initial condition, and we'll get 1. So I believe our solution to this should be that right there, right? And more specifically, what we're going to do with Euler's method is not actually get a graph of the solution, but to find certain points. Now, if you find enough points, you can get a graph. But what we're going to do is just get a graph. So in other words, our problem is really going to be this. What does y of 2 equal? That's what we really want to know. That's what we're going to do with Euler's method. If y of 0 equals 1, and this is our differential equation, what does y of 2 equal? Well, we can tell that it's going to be what? We know that y of 2 is supposed to equal 5. So this would be like when we were doing our Riemann sums. This would be like if we did the exact integral, we know our exact area, and then we're going to look at our approximation and see how close we get. Okay, this is a very similar thing. So we know the solution should be this. We know that y of 2 should equal 5. But what if we couldn't solve this differential equation? What would we do? So we're gonna maybe sketch a little graph here. Put some values on there and so forth, and go through this. First, I want to show you a PowerPoint here that kind of gives us the big picture of how this is going to work. And it actually is going to go through the steps we're going to do, but we'll do that together later here on the board. So you don't have to write the rest of this down, the stuff that's on the PowerPoint here. Okay? So, all right. So let's go. What do we got? I mean, we got PowerPoints today. I'm using the tablet. I got the markers going. Calculators here in a minute. That's awesome. All right, Euler. 1707 to 1783, little history lesson. Euler made a huge number of contributions in mathematics, almost half after he was totally blind. When this portrait was made, he had already lost most of the sight in his right eye. I did not make up this PowerPoint. This was stolen off the internet from this guy right here. I actually heard this guy speak at a conference one time. So yes, I didn't really steal it. He kind of gave them to us. Said, here's my website where these are at. But pretty impressive. I mean, some of the art class thought they remembered him from Algebra 2 maybe or something. Talk about, and it might have been because of this, because he originated the use of these notation that we still use today. Function notation, E, that gave essentially the name of the base of the natural log, and pi. Oh, happy Pi Day, by the way. Forgot, yeah. Happy birthday, Jacob. On a lesser note, happy birthday, Jacob. There's Pi Day, and then there's Jacob's birthday. All right. Summation, sigma notation, and then this delta y, that delta y, delta x stuff, meaning, like I said, it could be delta y or delta x, but using that as a small change. And of course, we're going to use that here in this Euler's method. Delta y over delta x, that's, we've been using delta x for our width of our rectangles, change in x. We're going to talk about slope here with these difference equations. We're going to talk about change in y over change in x, rise over run. Okay? Now, here's what Euler's method does. If we got a differential equation we can't solve, we need to approximate it. Okay? Well, we'll do an easy one that we know how to do. So here's our differential equation right here. Now, again, keep in mind what we're trying to do. We know that we're starting at this initial value of 0, 1. So we know 1 point on the y graph. But the only other thing we know here is the slope. The only other thing we know is the slope. So we can plug that point in and we can get the slope. And that kind of tells us the direction the graph is going. That's what we did with slope fields. But how can we be better at it? How can we get actual points? Well, here's what we're going to do. We're going to kind of make a little bit of a table, and we're going to do something similar to this. The n column I wouldn't worry too much about. Think of that as your number of subdivisions, right? Okay. So they start out with 0, meaning this is our beginning point, 0, 1. And the only thing we can do is get our slope. So we're going to take our 0, we're going to plug it into our differential equation, and we get a slope of what? 0. So we get, ooh, that was cool. Do that again. All right. So we get a slope of 0. So we start at our initial point right there. We get a slope, we plug in our point, we get a slope of 0. So what Euler's method does is this. And see if you can see the connection to the rectangle. We say, all right, at that point we have a slope of 0. Let's pretend that the graph keeps that slope for a while. Let's pretend it keeps that slope for a while. Now what do left rectangles do? In approximating the curve, what do left rectangles assume or pretend?
That they keep that value.
That the curve stays straight, right? Horizontal for that value. What do trapezoids do? They pretend the graph stays linear, right? But the graphs usually don't, so that's why they're off a little bit. Well, that's what we're going to do here. We're going to calculate the slope, and we're going to pretend for a little while that the slope stays that. Now, how long is a little while? Well, it depends on the problem. And we're going to call that delta x. Guess what? That's the same thing we used in our rectangles. We called it the width, right, for a little while. So what we're going to do is, see down here in the blue, if you can, everybody can see that, we're going to take our slope, which is rise over run, and we're going to take it times our little y, our run, our delta x. And if we do that, that gives us our delta y, which is our rise. So this is one of the, probably the most important step of Euler's method, right here. Taking your slope times your run gives you the rise. So when we do that, of course in this case, since our slope is 0, we're not going to rise at all, right? And notice what they just put up here. You'll usually be given that in the problem. Just like in a rectangle problem, you're given the width, or at least you can calculate the width. They tell you you're going to do 4 rectangles, and if your width is 2, then your width is 1/2. If your total width is 2, and you have 4 rectangles, then your width of each one is going to be 1/2. So usually you'll be given it, or you can figure it. So we're going to go for a little while, we're going to go over 1/2. All right, and we're not going to go up at all, because the slope is 0. So the way we calculate that, obviously, is what point are we at? What y value are we at? We're at 1. We're going to add on our rise, which, of course, our rise right now is nothing. And that'll be our new y value. So our new y value will be the same old y value was before, which is 1. So now we got a new point, and there it is right there. So we calculate our slope as 0. We pretended it stayed that slope for a little while. Go to our new point. And there we are. Okay, now we're going to repeat the process all over again. So now we're at this point right here, 0.5 and 1. We're going to now calculate the slope. So we come back to our differential equation. We put our 0.5 right in there for x. We get what? 1. So our slope at this point now, the slope is 1. So we're going to pretend that the graph has a slope of 1 right now for a little while. Okay, well, we got to calculate our rise. So we take our slope, 1, times our dx, right? That's this little formula right here. Rise over run times run gives you the rise. So if the rise is 0.5 plus the y, we're already at 1. If we're going to rise up 0.5, we're going to now be at 1.5. And there it is. There's our new point. And we just repeat this process. Okay, so we're now at a new point. We're going to calculate our slope. Put a 1 in for x. Gives us a slope of 2. We're going to take our slope times our run. Gives us 1. That's a rise of 1. Add that on to the 1.5 we're already at. We are now at 2.5. There's our new point. Now we're almost there because look over here. I love it. I got the pointer going. Man, I don't think there's any piece of technology I'm not using today. Speakers. Okay, we'll have to get the speakers going. We'll listen to some music later when we're doing homework. All right. So remember, we're on our way over here to do y of 2. Well, right now we're at y of 1.5. We just got one more step to go. Okay, so we take our 1.5, we put it in, get the slope. That's 3. Take our slope times our run. Gives us our rise of 1.5. We were at 2.5. We rise up 1.5. We're now going to be at 4. And so our new point is up here. Now remember, we knew that the curve, look over here, we knew that the curve was actually dx squared. You can kind of see the parabola in there. Here's the exact solution. Okay, we already went through this. There's the blue. Why does the red not look like the blue? Why is it an approximation? Why is it not exact?
Because it's an approximation.
What did we do in the red? You guys already said it, and I said it. Why does the red fall behind or below the blue?
Because it keeps the same value for.
Because it pretended that it calculated the slope. They both have the same slope right here when we started, but the red one pretends that it keeps that slope for a while, and that makes it be off. How could we make the red better? Smaller delta x, right? That is called, in Euler's method, that's called the step size. The delta x is called the step size, but it's the same thing with rectangles. Smaller and smaller steps, and that's why we study it right now when we're doing these other things. Very same idea. Smaller and smaller step size, we would get a better red graph. It would look closer to the blue. Get the calculators out, Tori, you're on. All right. So, on the quiz. And we're gonna go through this here on the board here in a minute. But on the quiz, there are going to be some problems where you're going to have to write out kind of that table like we just did up there. Now I'm going to do that on the board so we can all go through it together here in a second. We're going to use the same rule. If you've got less than 10 steps for Euler's method, you're going to write it out. If you got 10 or more steps, you get to go to the calculator. So let's say that instead of doing a step size here of 0.5, right? Now think about the step size of 0.5. On the quiz, I might tell you the step size is 0.5, or I might tell you do 4 steps. In this problem, how would you figure the step size? Well, if you're going from 0 to 2, and you're going to do 4 steps, 2 divided by 4 is 1/2. That's how you get the step size. Same way we get the step size in the other one. But what if I told you to do a step size of 0.1? From 0 to 2, step size of 0.1, how many steps is that? 0 to 2, step size of 0.1, how many steps is that? 20 steps. You do not have to do 20 steps by hand. You'll get to use your calculator. Here's how we do it on the calculator. Go to the graph screen. You want to delete out any graph that's already there. Control Delete will clear it right away. Hit Control Delete, that'll hit clear, hit Enter. Okay, so clear out any graphs that are there. All right, now go to your menu and go to Graph Type and choose Differential Equation. Everybody's got to be able to do this for the quiz on Friday. Okay? Notice it gives you a differential equation window here. You notice you got a y1 prime. Everybody should have that as everybody's blank. If it's not, clear it out. Down here you got x sub 0 and y1 sub 0 means you have a, that's where your initial condition goes. Now I will warn you that if your differential equation has y's in it, this is for your homework now today, and if you're going to use your calculator on any of them, if you have more than 10 steps, you have to type in y1 anywhere you have a y. Okay? And if the difference equation has t as its input, you have to put x when you do the graph. So you have to use x and y1 when you type these in. Okay. But for ours, easy because we already knew it's 2x. So go ahead and type that in. So you got y1 prime equals 2x. Tab down here and put in your initial condition, 0 and 1. Okay, go ahead and hit Enter. They get a slope field. Now, on Tori's we can't see any points, but that's because of her window. Okay, so let's go into the window settings. And I would probably have already, in the problems, I'll probably give you some window settings, but if you just go, let's go -5 to 5, be fine. And then hit Enter. And then maybe Zoom Fit might be a good, I don't know if Zoom Fit will be very good. Yeah, that's pretty good. Okay? Now notice you don't get a solid graph, but you get a bunch of dots. Well, the calculator is also using Euler's method to calculate these dots, because the calculator does not, I mean, it could probably do an antiderivative thing, but some of them don't have solutions, so it doesn't do that. Okay, so it's using the same kind of way to get these graphs. It's actually plotting a bunch of points. Now, what we need to go into here, go back to your equation. Control G is the fastest way to get back to your equation. Control G. And then tab. Tab?
Yeah.
Guys, I always say that, and then you guys remind me tab. Okay, tab will open that up also. Thank you. Then you got to arrow up to that Y1. I can never remember that. Now, right over here, now you guys, hopefully somebody can find a faster way for this. I haven't looked very hard, but this little box right over here on the right says Edit Settings or Edit Parameters. You want to click on that. I'm not sure if there's a faster way to get to that or not. All right, and then this comes up. Now, go to under the Euler one, click on the little button, or click on the little triangle there. There's Euler and there's Runge-Kutta. Now, those are just two different methods. We've learned Euler's method, but that's like Simpson and trapezoid. There are two different ways to get rectangle areas. Runge-Kutta is better and more accurate, but it's more complicated to understand, I think. I don't know what it is, to be honest with you. So we're going to do Euler. So keep it in Euler. Keep it in Euler. Okay, matter of fact, keep all of these the way they are. Keep that a 1, slope. All of these we're not even going to mess with, except plot step. That's the one. That's our step size, okay? This delta x, our step size, is plot step right there. So put in 0.5 first. And let's just show that we get those same values we came up with in the PowerPoint. So go ahead and click OK. Put in your 0.5. Okay? 0.5. Click OK. All right, now let's go to trace. And this is how you're going to find the values, is just by tracing. Now you can also go to the table. Somebody was talking about going to the table. You can do that. But let's trace. And now watch what happens as you trace to the right. You're at 0. Then you're at 0.5. Then you're at 1. And notice you're getting those same values we had in the PowerPoint. Okay, keep going all the way to 2. Okay, stop. Go back. Okay, see how you get the 0.24? Go back one. 1.5, 2.5. Remember, those were the same values we had in the PowerPoint. Because the calculator has calculated them that same way. All right, go back to your parameter settings and change the step size to 0.1. Got to be a shortcut to get to those settings. Change the step size, the plot step, to 0.1, and now this should be more accurate. So now when you trace, notice you got more dots. And now when you trace, it goes by 0.1. And when, sure enough, when you get to 2, what do you got? 4.8. That's closer, right? We knew it was supposed to be 5. We're getting 4.8 instead of 4. It's more accurate. Okay? Smaller the step size, the more accurate our approximation. All right. So that's what you do if you have 10 or more steps to do. You can just graph it, trace, write down the answer. All right. So now in your notes, let's go to do this together here, what it would look like on the ones you have to write out by hand. So we're just going to do right now what you saw in the PowerPoint. So here's the problem. We got y prime equals 2x. We're going to make ourselves a table. It's basically going to have 5 entries in it. Okay? I'm not going to do that end column that they did. So we're going to start with our initial condition. Okay? What's the first thing we can do then? Really the only thing we can do is what? Get our slope. I mean, all we have is a differential equation, the y prime. All we can do at this point is our y prime, which is our slope. Okay? So we take our x and our y. In this case, all we need to plug in is x. We plug our 0 in. 2 times 0 is 0. So our slope is 0. There's 2 more columns. What's the next column? That is the rise. We get that by taking our slope times delta x. Our rise, or delta y, is gotten by taking our slope times our delta x. There's your slope. Our delta x is 0.5. It's given to you, or you'll calculate it based on b minus a over n. And of course, we get 0. So our rise is 0. Last column, and you wouldn't have to have this column probably, but your new y. Your new y is the old y plus the rise. The old y plus how much you rise. So we rose 0 from our old y of 1, so we're still at 1. So now what's my next x over here? What do I got right here? 0.5. Now, I'll be honest, that usually confuses people. What I usually do is fill that in first. When I make my table, I say, hey, my delta x is 0.5. I'm starting at 0. What I normally would do is I would just go in here and I would fill in my x column right away. And just because I know what they're going to be. Now I don't have to worry about it. So now my new y is 1. So I just come down to my next row and I stick that right there. So that's the point I'm now at. And you can imagine what's happening based on what we did on the PowerPoint. We went from there to there. So now what? We need our slope. So we take our 0.5 and we plug it into our differential equation. 2 times 0.5 is 1. Next column is our rise. So I don't want you to get so bogged down in the details of the column that you forget the big picture. But you have to kind of know what to do as well. So we take our slope times our delta x. That would be 0.5. So our new y is our old y, 1, plus our rise, 0.5, we get 1.5. So we're now at the point 1, 1.5. So we've now went up like that, just like we did on the PowerPoint. Take your x of 1, plug it into the differential equation, get a slope of 2. Take your slope 2 times your step size. Slope times run gives rise. That's a rise of 1. 1.5 plus a rise of 1 is 2.5. So we're almost there. We know we're headed to do y of 2 is what we want. We're almost there. Take our x, 1.5 times 2, slope of 3. Slope times step size is 1.5. That's our rise. Our old y, 2.5 plus our rise, which is 4. And we got it. Last thing there is where we're at. Y of 2 is equal to 4. Y of 2 is equal to 4. And so, okay, so that's 4 steps. That'd be 4 Euler steps to find that y value. So it's more accurate than slope field. And we can make it more accurate by making it smaller step size. And at some point, though, we have to just rely on the calculator to do it for it. Okay? Because it's programmed in to do it. All right, your assignment is the bottom section. You guys missed out on the tornado drill, but they had like 7 minutes to work on their homework, and you got like 40. So I guess that's not a bad thing.
That's fair.
All right, so the bottom line, there's some problems in there where you have to write out the table, okay, if it's less than 10 steps. If it's more than 10 steps, graph it on your calculator. Some questions that ask you kind of about the overall process. All right, better get some music playing.
Never use the phone.
What's that?
Look at that shit.
Phone?
Never use the phone.
What phone? My phone? Oh, wait, we got it.